Okay, so this is probably the most important part of this chapter. And this is solving logarithmic and exponential equations. So typically we have x as an exponent or the argument of a log. And we want to find out what x value satisfies the equation. So there are you can use the inverse properties of logarithms and exponential functions, and also sometimes the properties of logarithms. So sometimes you can kind of work them out, kind of use kind of reasoning techniques, but then there are some other more straightforward ones. So for example, this first problem, what power do I raise 8 to get 4? And you can kind of think about how you might do this by knowing that if you had to the first power, you'd have 8 to the first power would be 8. 8 to the negative 1 power would be 1/8, 1 over 8. Or if you took the half power, you'd have the square root of 8, which would be 3 point something, 2 point something, because 3 squared would be anyway, the square root of the square root of 8. If I said what is the square root of 8, that ends up being 2 point something, 7, I think, approximately. So if you took 8 to the 1/2 power, you'd have less than 4. So we know it's more than a half and less than 1. Another way to think about this is if we wanted to, this is equal to 2 squared. 4 is 2 squared, and 8 is 2 cubed. So you'd have 2 cubed to the x power, like that, and then you can multiply the exponents together because you're raising one to the other, so you'd have 2 to the 3x, and you'd have 2 to the second power. And so now that you have the same base, you could just set the exponents equal to each other, and you'd get x to the 2/3 power. So that would be one way of doing it. The other way of doing these when you're solving exponential problems is to take the logarithm of both sides. And what you do here is use the properties of logarithms to simplify the right-hand side. So anytime you take the logarithm of something that's an exponential, you can bring out the exponent. So you'd have x is equal to the natural log of 8. So the exponent becomes the multiplier in front. And then you could solve for x. So you'd find x is the natural log of 4 over the natural log of 8. And if you plug that into your calculator, you should get 2/3. So let's see what happens. The natural log of 4 divided by the natural log of 8. And the answer you get is 0.66, which is 2/3. Now this is the more straightforward way. So again, any problem that has an exponent, you can use this technique. I'm trying to add a page here. I'm not sure my cursor's acting a little weird here. But anyway, looking at number 2. So let's do the easy way first. So if you take the natural log of 3/4 to the x is equal to the natural log of 27 over 64. So you get x times the natural log of 3/4 is equal to the natural log of 27 over 64, or x is equal to the natural log of 27/64 divided by the natural log of 3/4. So if you plug that into your calculator, make sure you use a parentheses too when you do the natural log left parenthesis 27/64, right parenthesis, and then I do the natural log of 3 divided by 4, and I get 3 is the answer. Now the other way of thinking about this is that you would try to rewrite this left-hand side such that it's 3/4 to some power. So 27 is 3 cubed and 64 is 4 cubed. So when you have 3 to the 3 cubed over 4 cubed, that's 3/4 cubed. And you see that now that I have the same base, I can set the exponents equal to each other, and you get the same answer. Okay, and kind of what this, what these series of problems are looking at is they're trying to make it so that you end up with the same argument here like in the natural log. So 3 is obviously x equals 2, because if you have the natural log of 2 minus the natural log of 2, that should be equal to 0, anything minus itself. So as long as, or you could also write it natural log of x is equal to the natural log of 2, and for the natural logs to be equal, the arguments of the natural log have to be equal to each other too. The other way you would solve this problem is you would kind of do the opposite, because we're starting with logs instead of exponents. So you could still end up with the natural log of x equals the natural log of 2, and then if you take e to the natural log of x and e to the natural log of 2, when you have e to the natural log of something, because of the inverse properties of exponentials and natural exponentials and natural logs, it just becomes x, and the same thing over here. So you get the same answer, x equals 2. Now the fourth one, this one to get this, how do you get this, the right hand side written as e to some power? That's the hard part here. So in this case, I would probably just use the more straightforward method. You take the natural log of both sides. Natural log of e to the x is just e x times the natural log of e, and the natural log of e is 1. So you get x is equal to the natural log of 2. And if you think about it, if you take e to the natural log of 2 and you stick that in your calculator, so it's the exponential function raised to the natural log of 2, you should get 2, which you do. So that confirms that this is a solution. You get to take the solution, you stick it back in your original equation, see whether the equality holds. So e to the natural log of 2 is 2, so you get 2 equals 2. And therefore you're sure the thing is working. Okay, number 5 is the natural log of -1. That one, there's a couple of things that, well, yeah, it's the same, kind of the same one that we just did. Same kind of arrangement, except you make each side of this equality be the exponent, because if the exponents are equal, then certain base raised to the exponent. Now you choose the same base as for the logarithm as for the exponent. So if I had like log base 2 of x equals -1, I'd have 2 to the log base 2 of x is equal to log base 2 of -1. Is that right? No, it would be 2 to the -1, 2 to the -1 power. So you have the same base. When you have the natural log, you want to have e as the base. E is 2.71828. Okay, e to the natural log of x is x, so you get e to the minus 1, which is 1 over x. Again, you can plug that back in. If you did the natural log of 1 over e, and you plug that in your calculator, the natural log of 1 divided by e, and you get negative 1. So the left-hand side, right-hand side is negative 1. If you evaluate this, you get negative 1, so you get negative 1 equals negative 1, and so you know you've solved the problem correctly. So number 6 is going to be similar to this, except the base is no longer e, the base is 5. So you take 5 raised to the log base 5 of x, and then you'd have 5 raised to the negative 3 power. So because the base here, the exponent, the base, the logarithm are the same, they're inverses of each other, therefore f of g of x is x. And over here you get 5 to the negative 3, which is 1 over 5 to the third power, which is 1 over 125. Now to check this, you'd have to take log base 5 of 1 over 125, and to be able to use your calculator, you'd have to use the change of base, which you'd take the natural log of 1 over 125 divided by the natural log of 5. 5 is the base. So let's just see if that works or not. The natural log of 1 divided by 125, the whole thing divided by the natural log of 5, and I get negative 3, which is equal to negative 3. So I know I've done that one correctly. Okay, so those are some simple examples of solving for x, when the x is either exponent or the argument of a logarithm. Okay, it says here, approximate the points to the intersection of the graphs of f of x and g of x. So the blue curve is g of x equals 8, f of x equals 2 to the x. So anytime you're trying to find the intersection of two functions, you just set the functions equal to each other. So at this point where they intersect, f of x equals g of x. So for number 7 here, we're saying the intersection is where f of x equals g of x. So if I plug f of x, I'll get 2 to the x is equal to 8. Now you may be able to just say, oh, it's 3 because 2 cubed is 8, but let's use the one we don't have to think so hard. So this is an exponent, so what that means is we're going to use the natural log. Take the natural log both sides. Properties of logarithms says I can bring the x out front, the exponent out front, and then I divide both sides by the natural log of 2 to solve for x. And then if you plug that into your calculator, natural log of 8 divided by the natural log of 2, and I should get 3, which I do. So that's, and if you look at it, you'll see that x equals 3 is the x value where they equal each other. Okay, let me delete this page. So the next one is a similar situation. This red curve is 27 to the x. G of x is the green line, the blue line, which is a horizontal line. So to find the intersection of the two, we just set the two functions equal to each other and say, what is the value of x for this to work? Again, it's an exponential equation, so we use the opposite the inverse of the exponential, which is the logarithm. So you take the natural log of 27 to the x, natural log of 9, bring the exponent out using the properties of exponents, divide both sides by the natural log of 27. So if you take the natural log of 9 divided by the natural log of 27, you'll get 0.66, which is 2/3. You can check this, so 27 to the 2/3 power, 27 raised to the 2/3 power, ends up being 9, which is what the original equation said. Okay, one more here. So we're looking for the intersection of the red curve, which is the log base 3 of x. You can see the log of 1 is 0, the log of 3 is 1. So here's 3. If you look down here, here's x equals 3, y is equal to 1, and the log of 9 should be 2, which actually gives you the answer, but let's show you how you would do it. So again, what you do is you use the inverse property of logarithms, which is exponentials. Now for solving these exponential equations, we can use the natural log, but to solve the logarithmic equations, we have to use the same base as the log base of the logarithm. So we wouldn't do e to the log base 3 of x. That wouldn't work because this base is different than that base, so that's not going to work. What we do here is we use the properties of logarithms to solve the other problems, whereas here we're not using the properties of exponents or anything like that. So what we'd have to do is 3 to the log base 3 of x equals 3 to the second power, because what we're doing is we're saying log base 3 of x equals 2, so we make this the exponent with the base being the base of the logarithm. So 3 to the log base 3 of x is just x, and 3 squared is 9. So you get x equals 9, which corresponds to the correct answer there. Okay, so now we're looking for the intersection of x equals 0, y equals 0, and this log. So let's write that out. So we just set them equal to each other, just like we have before. So here we have a logarithm. So we're going to make this the exponent of the same base as the natural log. Well, the base of the natural log is e. So we take e to the natural log of x minus 4 is equal to e to the 0. So you can see these become the exponent. You use the inverse properties of logarithms and exponents of the same base. So these are the same base. So the left-hand side just becomes x minus 4. And e to the 0 is 1. Anything raised to the 0 power is 1. And then you add 4 to both sides and you get x equals 5. And you can see that's what we get down here. If you look at here's x equals 5. That's where the two curves intersect. Okay. Solve the exponential equations algebraically. Approximate the results to 3 decimal places. So these are similar. In all cases, we have to solve for the exponential by itself. 3 to the x, e to the x, e to the x. And once we do that, then we can use the inverse properties of logarithms and exponentials. So this first problem, first thing we're going to do is we're going to divide by 4, because that's just a constant. So 20 divided by 4 is 5. Now we have an exponential equation without any constants in front of it. It's just the base to raise to some power. So again, for exponential problems, which these are all exponential, we can use the natural log. We could use log base 10, but we're going to use the natural log. So we take the natural log of both sides. You can bring the exponent out front, divide by the natural log of 3. So the answer x is the natural log of 5 divided by the natural log of 3, which is, and it says 3 decimal points, so 1.46. Okay, the next one, we have 4e to the x equals 91. So we divide both sides by 4. So 91 divided by 4 is 22.75. Again, for exponential equations, we can use the natural log for every one of them. In this case, it works out great because we have e to the x, they're the same base, but they don't have to be in this case. So you bring the x out front, the natural log of, so you get x times the natural log of e is equal to the natural log of 22.75, and the natural log of e is 1. So you get the answer is the natural log of 22.75. So we plug that into our calculator. Natural log of 22.75 is 3.12. And you can check the answer. So if you take 4e to the 3.12 and put that in your calculator, 4 times e to the 3.12. Now it's not going to exactly be 91 because I'm only carrying it out to 3 decimal points, but I get 90.6. So it's close to 91. If you used all the decimal points, you get much closer. Okay, 13. We have to do a little subtraction here. Here all we had to do is divide, but in this case on 13 we'll add 9 to both sides. So now we've got an exponential equation by itself without any constants in front of it. Everything else is on the other side, so we're going to take the natural log of e to the x is equal to the natural log of 9. The natural log of e to the x is just x, and so the answer is the natural log of 9, which is 2.20, 2.197224577. Okay, 14, we got 6 raised to the 5x power is equal to 3,000. So we don't divide by 6. You can't divide, if it was 4 times 6, then we divide by 4, but in this case we're not multiplying by anything. We just have this thing to the base. Now, again, you might think I have to use log base 6, but I don't. I just have to use either any base of log, and the easiest one to use is the natural log. So you can take the exponent out. So you get 5x times the natural log of 6 equals the natural log of 3,000. Divide both sides by 5 times the natural log of 6. So you get the natural log of 3,000 divided by 5 times the natural log of 6. Plug that in your calculator. And I get 0.894. Okay, so let's double check here. 6 to the 5 times 0.894. So 5 times 0.894. That's 6 raised to the 4.47 power. So we can do that on our calculator. 4.47. And I get 3,008. Again, that's 4th decimals just because I've rounded off my answer here to 3 decimal points. Okay, then we have 15. So again, even though the base is 4 for the exponent, we can use any log. Now, just to be different this time, I'm going to use log base 10 because that's the other one that's on your calculator. So you have log base 10 of 4 to the minus 3t power is equal to log base 10 of 0.1. So this is log on your calculator if it doesn't have a 10 to it. If it's ln, it's natural log. If it's log base 10, it's either log or log with a subscript. So again, the properties of logarithms says it doesn't say what the base has to be. It can be any base. You just take the exponent, move it out front. And then I can divide by 3, and I can divide by negative 3. So I divide by negative 3, and I can divide by log base 10 of 4. So I'm going to use the log here, the log of 0.1 divided by negative 3 divided by log base 10 of 4. And so I get t is equal to 0.554. And then just to check my answer, so I'm going to do over here. So you have 4 to the negative 3 times 0.554 power. So 4 raised to the negative 3 times 0.554, and I get 0.1. So this ends up being equal to 0.1 approximately. I get 0.0998, but if you round it up, it goes to 0.1. So that checks out. Okay, so these are all exponential ones. You want to solve for the exponent term by itself. So in these cases, I had to divide by 4 to get just the exponent by themselves. This one's by itself if I move the 9 to the other side. This one's already set to go, this one too. And then you can use the natural log, you can use the log base 10, and then the properties of logarithms. So the next bunch I think is some more, okay. So again, number 16, I have just 2 raised to some power, so I don't have to do anything else. So I'm going to take the natural log of 2 raised to the 3 minus x equals the natural log of 565. So you take the exponent, which is 3 minus x, multiplied by the natural log of 2. So what we want to do is solve for x. So the first thing we'll do is we'll divide by both sides by the natural log of 2. And what that leaves is 3 minus x. So I want to solve for x. So if we subtract 3 from both sides, we'll have negative 3 plus the natural log of 563 over the natural log of 2. And multiply everything by negative 1, so we'll get x is 3 minus the natural log of 563 over the natural log of 2. So plug that in. 3 minus the natural log of 563 divided by the natural log 2. So I get negative 6.14. So let's check out 16. Plug in. So if we plug in 3 minus x, where x is negative 6.14, so that's 2. So you have a minus times a minus. It's a plus. So 3 plus 6.3. So you get 3 plus 6, which is 9, 9.14. 2 raised to the 9.14 power is, I get 564. So that's close enough. Okay, the next one, I've got this multiplier in the front, so I'm going to have to get that out of there. So the first thing that I would do is divide by 3, both sides. So that leaves 5 to the x minus 1 is equal to 7. Now I have the exponential term by itself, so I can take the natural log of 5 raised to the x minus 1 power is equal to the natural log of 7. Bring the exponent out. Divide both sides by the natural log of 5. Add 1 to both sides. And you get 1 plus the natural log of 7 divided by the natural log of 5. And I get 2.21. And again, if I plug that in here, I'll get 3 times 5 to the 2.21 minus 1. So that's 3 times 5 to the 1.21. 2.21 minus 1 is 1.21. 3.5 raised to the 2.21 power. 1.212. So 3 raised to the 1.21 power is 4.5. Oh, and then I got to multiply by 3 times 3, and I get 13. Oh, something was wrong. What did I do wrong here? Oh, I know what I did. I just put it wrong in my calculator. So 3 times 5 raised to the 1.21 power, and I get 21. So this 3 times, I did 3.5, 3 times 5 to the 1 point, that equals 21.0. So these are equal to each other, so I've checked it out. I check my solution. Okay, number 18, I've got e to the 2x equals 50. Again, it's an exponential problem, so take the natural log of both sides. Natural log of e to the, so since these are the same base, we can use the inverse properties of logarithms and exponentials of the same base. So here you get 2x equals to 50. I got to take the natural log of both sides, which I didn't do. Natural log of 50. So this left-hand side just becomes 2x. The right-hand side is the natural log of 50, so x equals the natural log of 50 divided by 2. So the natural log of 50 divided by 2 is 1.96. If I plug that back in here, e to the 2 times 1.96, which is e, 2 times 1.96 is 3.92, e to the 3.92 power. And I get 50.4, which is close enough given the rounding. Okay, now the next one we're going to have to do a little bit before we use the inverse properties. We want to take the 7 and put it on the other side. So what you'll have on the left-hand side is that second expression, negative 2e to the x. And what you'll have here is 5 minus 7, so we subtract 7 from both sides, so that's negative 2e to the x equals negative 2. If you divide both sides by negative 2, you'll get negative 2 divided by negative 2, which is 1. And then you can take the natural log of e to the x equals the natural log of 1. The natural log of e to the x is x. And the natural log of 1 turns out to be 0, so you get 0. And if you plug this back in, e to the 0 is equal to 1, so you get 1 times negative 2, and 5 minus 7 is negative 2, so that all works out well. So that was number 19. Number 20, same kind of deal. So what we're going to do is we're first going to get the exponential term with the constant by itself. So we're going to add 14 to both sides. So 11 plus 14 is going to be 25. So you can also say negative 14 moved to the right-hand side becomes positive 14. 11 plus 14 equals 25. Okay, we still don't have this by itself. E to the x equals 25 over 3. Then you take the now you can take the natural log of both sides. So we get the natural log of 25 thirds. Natural log of e to the x is x. And the natural log of 25 thirds is 2.12. And again, if I stick that in, negative 14 plus 3e to the 2.12 power. So that's negative 14 plus 3 times, so we take e to the 2.12 power. So that's 3 times 8.33. So you get negative 14 plus, well, 3 times 8.33 is 25. 25 minus 14 is 9. And that's what we expected. Actually, it's 11. Yep, it's 11, not 9. 25 minus 14 is 9. I mean, 25 minus 14 is 11. So that says that works. And do we have any more? One more. So again, a little more math, but what we're trying to get to is 4 to the 6 minus 2x is equals something. And then we can use the properties of logarithms. So first thing we do is we would subtract 13 from both sides. So this goes to 0. So you'd have 41 minus 13, which equals 28. Okay, now I need to get rid of this constant out front, so I'm going to divide both sides by 8. So 28 divided by 8 is 3.5. Now I have 4, the base raised to some power. So take the natural log of 4 raised to the 6.6 minus 2x equals the natural log of 3.5. So in this case, we don't use the inverse properties of the natural log and 4 because they're not the same. We use the properties of logarithms, says you can bring the exponent out. So to solve for x, the first thing we'll do is we'll divide both sides by the natural log of 4. So the natural log of 3.5 divided by the natural log 4, you get 0.904. And then we'd subtract 6 from both sides. So this goes over to the other side. Subtract 6, we'll get negative 5.09. And then we'll divide both sides by negative 2. So you'll get 2.54548, or rounded off to 2.55. And let's just go over here and check it out. So you have 8 times 4 to the 6 minus 2 times x, which is 2.52 plus 13. Okay, need another parenthesis there. Okay, so you have 8 times 4, so you've got 6 minus 2 times 2.52. So that's 4 to the 0.96 power plus 13, and 4 to the 9.96 power, 4 raised to the 0.96 power is 3.78 plus 13. So take 3.78, multiply by 8, add 13, and we get 43. Okay, so something's wrong. What did I do wrong? So let's see if I've put the right number in here. Okay, so let's go back and check this thing out. Okay, 8 times, okay. So we subtract 13 from both sides. 41 minus 13 is 28. 28 divided by 8 is 3.5. The natural log of 3.5 is 1.25. And we divide by the natural log of 4. 0.904. Then we subtract 6. We divide by 2. And what I'm going to do is just leave all the decimals here and make sure it's not just because I rounded off. Yeah, so I got 2.55. So let's see if that fixes it here. So I did 2.52, 2.55. Go over here. Okay, so 6 minus 2.55 times 2. 6 minus 2 times 2.55. So I get 0.9. So 4 raised to the 0.9 power. You get 3.48. 3.48 times 8. 27 plus 13, so I get 40.8 something, which matches up better. So it was my third digit there that I got incorrect. Okay, the next bunch are, well, I'm still working on. Yeah, there's a lot of problems here just because you got to do a lot. So again, what we need to do is solve for this e to the 2x. So we have to do the algebra to make that work. So the first thing I would do is I would make this into a ratio. Instead of 2, I'd have 2 divided by 1. And what that means is I can interchange these two. So I can move that to the denominator. I can move that other part to the numerator of this other side. So 3,000 divided by 2 is 1,500. Then I subtract 2 from both sides. And now I'm just going to switch sides. So now I've got it. So I've got e to some power. So now I can use the natural log. Natural log of e to the 2x equals the natural log of 1,498. So e to the natural log of e to the 2x is 2x. And the natural log of 1,498 is 7.3119. I'm carrying some extra digits here. Then divide both sides by 2. You get 3.6559. So let's double check that. Put that back in here. So we have 3,000 divided by 2 plus e to 2 times 3.6559. And hopefully that's equal to 2. So you get 3,000 divided by 2 plus e to the 2 times 3.6559. And the answer is 2, which is correct. Okay, 23. Same kind of deal here. So we just have to do some algebra first. So the first thing we do is probably just go ahead and evaluate what's in the parentheses. So you'd have 4 minus 2.471 divided by 40. So there you get 3.938 raised to the 9t power is equal to 21. And so here's our base. It's not an integer, but doesn't have to be an integer. We again use the natural log here. So we take the natural log of both sides. Natural log of this to this power is that power times the natural log of 3.938 is equal to the natural log of 21. So if we solve for t, we're going to divide the right-hand side by 9 times the natural log of 3.938. And we'll just plug that into our calculator. And I'm just going to give you the answer. We'll assume it's right, 0.247. And then the last one here is 24. So we've already got this by itself, so that we really don't have to do a whole lot. So you can take the natural log of e to the 0.09t is equal to the natural log of 3. Natural log of e to that is just the exponent. 0.09t is equal to the natural log of 3, or t is equal to the natural log of 3 divided by 0.09. So that is 12.2. And again, we can check that out. E to the 0.09 times 12.2. So 12.2 times 0.09 is 1.098. E to the 1.098. And then we'll check it on our calculator. 1.098. And I get 3, which checks. Okay, so the next bunch are all logarithms. Now the difference here is that I have to use exponential functions, but I have to use the same base. The base of the exponent has to be the base of the logarithm. And to be able to do that, I have to get the logarithm by itself. So this one's by itself. There's no constant in front. This is by itself. This one's got 6, so I'm going to have to divide both sides by 6. This one I have to divide both sides by 5. So 25, the logarithm is the base e. So I take e to the natural log of 2x and then e to the 2.4 power. So this is where you have the inverse properties of logarithms and exponents. So e to the natural log of 2x is just 2x. And then if I take e to the 2.4 power on the right-hand side, I'll get 11.0 and then divide both sides by 2 and I get 5.51. Okay, 26, same kind of deal. This is log base 10, so the base is 10. So I take 10 to the log base 10 of 3z is equal to 10 to the second power. So these just become the exponent of the base, which is the base of the logarithm. So 10 to the log base 10 of 3z is just 3z. And 10 squared is 100. So z is equal to 100 divided by 3, which is 33.3. Okay, here we have log base 3. So first thing we're going to do is we are going to divide both sides by 6. So we get 1.83333. Then you use a base of 3, and the exponents are the left and right hand side of the original expression. So you take 3 to the 1.8333. 3 to the log base 3 is just of 0.5x is just 0.5x, and 3 raised to the 1.83333 power is 7.494. Divide both sides by 0.5, which is the same as multiplying by 2. So you'll get 14.99. And then 28, same kind of deal. It's log base 10, so the exponential we're used is 10 raised to some power. But first, we've got to solve for log base 10. So we need to divide both sides by 5. So 11 divided by 5 is 2.2. And then you take 10 to the log base 10 of x minus 2 is equal to 10 to the 2.2 power. So 10 to the log base 10 of x minus 2 is just x minus 2. And 10 to the 2.2 power should be more than 100. It's 158.5. And then we add 2 to both sides. So we get x equals 160.5. Now we do have log base 10 on our calculator, so if we take the answer, subtract 2 from it, and then take the log of that of 158.5, we get 2.2, which is 11/5. Okay, so this is our last bunch. Now here we have something interesting because we have this exponent, but it's not that different. What we do is we rewrite the square root as a fractional exponent. Then what I can do is I can bring that exponent out using the properties of logarithms. And I've got to get my for some reason my cursor stopped working there. Okay, so you bring the exponent out, so you get the natural log of x minus 2 is equal to 1/2. Bring that out, multiply both sides by 2. So this becomes 1/2 times 2 is 1. 1 times 2 is 2. Now you can use it again. The base of the exponential expression has to be the same base as the logarithm. So the base of natural log is e. E to the natural log of x minus 2 is just x minus 2. E squared is 7.389. Add 2 to both sides, you get 9.389. Again, we have the natural log in our calculator. So if we take the natural log of the quantity 9.389 plus 2, raise that to the 1/2 power, take the square root, close the parenthesis, and we get 1.2. So that didn't work out. if I did this correctly. Okay, I'm not getting 1, so let's go back and check it again. So bring that out. Multiply both sides by 2. E to the natural log of that is e squared. And add 2 to both sides. Oh, I see what happened. I copied this wrong here. This is plus 2. That's why. Okay, so we got x plus 2, so this is 5.389. Okay, so let's put in 5.389 instead of 9.389. So 5.389 plus 2. Take the square root of that. Take the natural log, and you get 1. You get the right answer. Okay, can't find my cursor. Where is it? Oh, there it is. Okay, next one, we need to solve for the natural log of x before we can use any inverse properties of logarithms and exponents. So we subtract 7 from both sides. So 5 minus 7 is negative 2. We divide both sides by 3, so we get negative 3 2/3. So now we got the natural log of x. So again, the base of the exponent has to be the same as the base of the logarithm. So you get e to the natural log of x equals e to the natural log of, or e to the negative 3/2. E to the natural log of x is x. So we have e to the minus 2 divided by 3. And so that's 0.5134. So let's just check it here. 7 plus 3 times the natural log of 0.5134. 7 times 3 times the natural log of 0.5134, and hopefully the answer is 5. I got something wrong here. Plus 7 plus 3 times the natural log of 0.5134, and you get 5, which is the right answer. Okay, now the next couple, you have to actually possibly solve quadratic equations. So and there may be 2 solutions, but you have to see which one makes sense, because the domain is that x has to be greater than 0, because if I have 0 here, I'll have the natural log of some positive number. If I put the natural log of 0 in here, I'll get a negative infinity. So in this case, the domain of the original function is that x has to be greater than 0. So if we get a solution where x is less than 0, then we have to ignore that solution. Okay, so the first thing we're going to do is we're going to combine these two using the properties of logarithms. So you have the natural log of AB is equal to the natural log of A plus the natural log of B. So what we can do is combine these into a product. So you get x times x plus 1. The natural log of the product is the sum of the natural logs. So now I've got natural log by itself. Again, the base of the exponent that I'm going to use to solve this is the same as the base of the logarithm. So when I take e to the natural log of this, I just have x times x plus 1. And on the right hand side I have e to the 1 power. And e to the 1 power is 2.71828. So if you multiply these out, you get x squared plus x and subtract 2.71828 from both sides, and you get this quadratic equation, which then you have to solve using the quadratic formula. So x is going to be minus b plus or minus the square root of b squared minus 4ac over 2a. So b is 1, so you get negative 1, plus or minus the square root of b squared minus minus 4 times a times c 2.7818. I think I got that written wrong. E to the 1 power. 2.7818. Oh, that's right. 2.71828 all divided by 2a. And what you see, if I take the negative square root, I'll get negative numbers. So I'm gonna take the positive square root because that'll give me in the domain. So in the square root, I'll have 1 squared plus or minus 4 times 1 times that. Okay, so it's going to be, the negatives will cancel out. I have 1 plus 4 times 2.71828. And then I take the square root of that. So I get negative 1 plus 3.446 divided by 2. So 3.446 minus 1 divided by 2 is 1.222. Again, I don't do the negative because I then end up with an x that's negative. So let's try that. The natural log of 1.222 plus the natural log of 2.222. So the natural log of 1.222 is 0.200, and the natural log of 2.222 is 0.798, and add those together and you get 0.998, which is approximately equal to 1. So that works. Okay, so the next one, similar situation. So you start with this. So we combine those two using the properties of logarithms. Then we have our base of e because we have the natural log, so we have e to the 1 again. E to the natural log of that is x times x plus 3, and then we have 2.71828 e to the first power. So we'll get x squared plus 3x is equal to 2.71828, and then you subtract 2.71828. You get a quadratic equation, and the solution is going to be minus b plus the square root, not the minus, because we get it again. X has to be greater than 0, so we're going to use the positive square root. So we have b squared minus 4ac all divided by 2a. So you'll get negative 3, and in the parentheses we get 3 squared. Again, the negatives cancel out. Negative 4 times negative 2 point something. So we'll get 4 times 2.71828, which is 19.87. Take the square root of that. So you get plus 4.458 all divided by 2. So 4.458 minus 3 is 1.45 divided by 2 is 0.998. is 0.729. And again, we'll check our answer out here. So the natural log of 0.729 plus the natural log of 3.729, so I'm adding 3 to it. So the natural log of 0.729 is negative 0.316, and the natural log of 3.729 is 1.316, which is equal to 1, which is the right answer. And finally, oh, we got 2 more. I got a headache here. So I'm grading all the physics tests today. Okay, now what we can do here is we can combine the 2 terms on the right-hand side. So because we're subtracting it, we put the positive expression in the numerator and the negative one in the denominator. Now, because these are all logarithms, we just say x plus 5 is equal to x minus 1 over x plus 1. So we didn't even have to use any properties of logarithms. We just had 2 logarithms on both sides. So then you multiply both sides by x plus 1. So we use FOIL, so you get x squared plus 6x plus 5 is equal to x minus 1. Move those to the other side and combine them, so you'll have 6x minus x, that's plus 5x, and 5 plus 1 is 6. So you get that. And it's not, just thinking about factoring that one. Can we factor it? Well, using the quadratic formula, you'd have negative 5 plus or minus the square root of 5 squared minus 4ac over 2a. So you get negative 5 plus or minus the square root of, so you get 25 minus 24, which is 1. So you get negative 5 plus or minus. Doesn't seem like that should work. What is wrong here? 2 numbers multiplied together give you 6 are going to be, oh, that's because you can factor that. Okay, I was like, I should have been able to factor that. I was taking 6 and 1, but the other option is 2 and 3, so you get that. And so you get x equals negative 2 and x equals negative 3. And the problem there is that if you plug in x equals negative 2, you're going to get the natural log of a negative number. So there is no solution to that. Even though I came out with a solution, the problem is that they don't work with the natural log domain. So that one's a little tricky if you don't think about it. And then the final one's similar kind of thing. We're going to combine these two together, and because they're both positive, we multiply them together. So that's just using the properties of logarithms to do that, and then we use log 3 as the exponent because I have log base 3. And then I have 3 to the second power. So these become the exponents. The base of the exponent has to be the same as the base of the logarithm. So 3 to log base 3 of this product is just the product. And 3 squared is 9. So we multiply that out, we get x squared minus 8x is equal to 9. And then we can subtract 9 from both sides to get that. And that one we can factor. It's x minus 9 and x plus 1 equals 0. So there's two solutions to this equation, x equals 9 and x equals negative 1, but that one doesn't work because if I plugged in negative 1 here, I can't take the log of a negative number. So we just take the positive solution, and then we can see if it works or not. So you have log base 3 of 9 minus log base 3 of 9 minus 8. And that should equal 2. Well, log base 3 of 9 is 2. What number do I need to raise 3 to get 9? 2. And here we have log base 3 of 1. Well, the log of 1 is always 0, no matter what the base is. So you get 2 minus 0, which is 2. So you get 2 equals 2, so it does check out. So what we found in these last 4 problems is that if you end up with a quadratic equation, the solution is the one that fits the domain of the original expression. So don't just automatically give both solutions.